And that's zoom out, zoom in, zoom out.
I need it.
And if you can adjust this to move it around. Alright.
Chapter 11 still? Chapter 12.
This is Chapter 12, Spectral Lines.
Oh yeah.
So you got to learn about spectral lines. And this is showing how spectral lines work. You see those lines on that screen? We call those spectral lines. Have you ever seen a rainbow?
Yeah.
That's a bunch of spectral lines together form a rainbow. So what we need to do is we need to understand what light is made up of, and how it is created. Yes.
Is red light hotter? I mean, colder than like blue light?
Red light has less energy.
Okay.
Yeah, because the waves have longer wavelengths. So it came from an object that was vibrating slower. If the object's vibrating faster, it creates shorter wavelengths, and that's more energy.
Very
Okay.
cool. Okay.
So what we need to understand is that what a photon is. A photon is a unit of energy, a unit of light. Okay? You can think of a photon as a particle that travels through space or through the room and is absorbed by your eye if you want to see something, or by some photographic film. The photons are released by atoms that are excited. And so what we have to do is we have to think about electron energy levels. Do y'all remember that electrons hang out at different energy levels? Like level 1 is the level closest to the nucleus, and level 2 is a little further out, and level 3 is even further out. Do y'all remember that? This is chemistry. Remember that? Okay, so when electrons like to hang out in the closest possible energy level to the nucleus. But what electrons can do is they can get excited and they can jump up to higher energy levels. Have you ever heard of that? Yeah. So an excited electron will, let's say I'm an electron, I'm hanging out at the lowest energy level and everything's just cool, and then I pick up some energy from elsewhere and I get excited and I jump up to a higher energy level. Electrons can do this. And then what they can do is they can jump back down to a lower energy level as well. So let me show you how this works. They're showing in this picture, they're showing an electron jumping down from the second level to the first level. When that electron jumps down, it has to release some energy. What it releases, the energy, as a unit called a photon. And it'll release the photon, and the photon will fly away. So if I'm an excited electron, watch up here, y'all. I'm an excited electron. If I jump down to a lower energy level, oh, you should have caught that.
Sorry.
I release a photon. Let me try it again. Okay? I'm excited. I'm at a higher energy level. I jump down to a lower level. I release a photon. Okay? That photon contains the amount of energy that I lost jumping down to the lower energy level. Throw it back. Now sometimes an electron can jump further.
Please.
An electron can jump even further, and it would release even more energy. I'm going to use this pen as an example. Now this pen is blue. Blue is at a higher energy level than green, right? So if I jump down 2 levels, I'm jumping down a long way. Now I'm releasing the blue.
Supposed to catch that.
You see what I'm saying?
I feel like 2 of y'all are going to catch it, but y'all are supposed to catch
Is it me still?
So 1, I release the green.
Oh, yeah.
2, I release the blue.
Give me the rock.
See what I'm saying?
Does blue go further than green?
Doesn't go further. They both travel at the speed of light.
Oh.
And they'll go through space until they hit something. But blue has higher energy than green. You see what I'm saying? So it depends on, I'm tired from all this jumping. It depends on how far it's going on what type of photon it releases. If it were to jump from the 4th energy level down, it might have to release a photon so great that it's not visible light anymore, that it's ultraviolet light or X-rays. You see what I'm saying? So light is produced when electrons jump down energy levels and release photons. How cool is that? So if you look at hydrogen, hydrogen emits these bands of light. It releases some red light, some light blue light, some darker blue, and some purple. Are y'all hanging with me? So why does it release only these 4 colors? This is hydrogen. Charlie, you gotta hang with me up here. Hydrogen, when it's hot, when it's glowing hot, it releases only 4 different colors. Red, light blue, dark blue, and purple. And why does it release those colors? It has to do with the hydrogen electron jumping down 1 level, or 2 levels, or 3 levels, or 4 levels. Releasing these different types of light. Take a look at this video. This tries to explain it.
If a sample of hydrogen gas is heated, it gives off light. When you view this light through a prism, you will see an emission spectrum consisting of bright lines at specific frequencies. Because the spectral lines come at definite intervals, this suggests that specific energy levels exist in the atom. A cross-section of an atom shows the energy levels similar to the rungs of a ladder. When energized, the electrons move temporarily to higher energy levels. As the electrons fall back to lower energy levels, they lose energy in the form of light, which produces the characteristic spectrum of the element. Because we know that the emission spectrum for each element is different, we also know that the distances between energy levels must be different for every element.
Okay, that went kind of fast.
Yeah, that was a little quick.
But let me explain what they're saying. So, whoops. So, there's different ways that you can jump energy levels. So I can jump from, if I jump from the top down, I might release blue. Blue is the highest energy. Okay? So I can go all the way down, I'm jumping down 2 energy levels, and I release blue. You ready to catch? I release blue.
There you
Okay,
go.
come back. There's another way I can do this. Okay, if I jump down from 1 energy level, I release red. Throw it back. Another way I can do it is I can jump down from the 2nd energy level to the 1st, and then down. So, how would I do that? Well, I wouldn't release a blue when I jump from the 2nd energy level to the 1st. I would release something different, because it's not as much energy as jumping all the way down. So I might release green and then red. And if you add up, that was a bad throw by me. If you add up the energy in the green and the red, it equals the energy in the blue. So there's 2 ways I could do it. I could jump all the way down from the top and release the blue, or I could, what we do, say a cascading. Cascading is where you go down in steps. So, green, red.
Oh, yeah.
Oh. See what I'm saying?
Red.
So, if excite, listen, if you excite a bunch of hydrogen atoms, hang with me here, pay attention up here. If you excite a bunch of hydrogen atoms that are jumping up 2 levels and then coming down, you will get 3 possibilities. You'll get it jumping all the way down from the 2nd level, blue light, that's up here. Or you can get it going to the 1st and then down, a green and a red. In this case, it's not a green, it's a light blue and a red. You see what I'm saying? So, when you excite a hydrogen atom, you get millions of atoms excited. Some are jumping all the way from the 2nd down, some are jumping to the 1st and then down. The ones that are jumping to the 1st and then down are releasing both green and red. The ones that are jumping all the way from the top and then down are releasing blue. And so you have several different lines of color that are being released. And that's why there are several different lines here. It depends on how far the electrons are jumping. Does that make sense? Helium doesn't just have 1 electron. Helium has 2 electrons going around its nucleus. And when you excite helium, those electrons, one of the 2 electrons might go up to 4 levels, one of the 2 electrons might go up 2 levels, and then cascade back down in different ways. And you end up getting more lines released by helium than you have released by hydrogen, because helium has more electrons. So the more electrons you have in your atom, the more different lines you might get. So look at helium spectrum, see all of its lines? That's more complicated than hydrogen's spectrum. It's only releasing a few lines. Now what this object looks like, if you're looking at it glowing, your eyes take in a combination of these photons. Your eyes will take in some red, and some light blue, and some dark blue, and some purple, and put all that together to make a certain color. And as a matter of fact, for hydrogen, there's a lot more red released than there are any of these colors, so glowing hydrogen looks kind of red. If you see something glowing red out in space, glowing red, it might be hot hydrogen. What's helium look like? Helium, there's a lot more of this yellow-green than anything else, so helium ends up looking kind of yellow when it's glowing. What's that?
I was just making sure when you were...
You like yellow color?
No, I was just making sure when you said something I repeated so I can remember it.
Good, that's fine.
Mr. Willis,
Yes.
if you were actually, if they were actually glowing, would that be explosive?
What would you be?
No, it just means it's hot. For instance, the gas in a light bulb is glowing because it's hot. That's why you see a light bulb glow. It's hot gas. Yes?
So it would only glow if it's hot, so if it's really cold, it would...
You wouldn't see it. You wouldn't see it glowing visibly. You could see it glowing in the radio spectrum even if it's cold. Make sense?
Yeah.
Are y'all with me here? Questions? Let's go on to something even more complicated. Nitrogen molecules. Now a molecule...
Wait, really quick, can you go back to the last slide?
Yeah?
Okay, because I was looking at my thing, you can't see the red on that.
Oh, the red there?
It shows up better.
Shows up better on your screen.
There's also
I can even see that, and I'm worse eyes than you. Let's get a little more advanced. Nitrogen, N2. Now this is not an atom, this is a molecule. And when we're talking about molecules, we're talking about sharing electrons. So when nitrogen shares electrons with another, and actually nitrogen N2 is sharing 3 pairs of electrons. Did y'all learn about
Have a bond.
shared electrons? It's called a triple covalent bond.
Oh, yeah.
It's the chemistry teacher would write it like that. because of the sharing of electrons, that makes the way the electrons jump up levels and jump down levels even more complex. The shared electrons jump up and down a little bit differently than a normal electron would. Imagine if you were jumping down off this desk, but you were also having to hold hands with somebody else. You might jump different distances if you were trying to jump down from high levels to low levels. If you're hanging on to somebody, you might jump different ways. The way the electrons interact is different when they're bonded to one another. So look at all of the different light, the different bands. There's a lot in the purple. There's a lot in the blue. There's still not many in the green and the yellow, but look at all the different reds there are. And this is, we're getting into the infrared, where your eyes can't even pick this up. But nitrogen emits at a lot of different levels, and so you get a lot of different lines. What color do you think glowing nitrogen gas would look, based on what colors, lines it'll give off? It'd probably look purple. That's a good guess, because it's got the red in it, and it's got blue in it, and red and blue together make purple. That's probably what nitrogen gas would look like.
That's a card.
Does this make sense? If you take something that's not a gas, that's a solid, the way the bonds work in solid objects makes it so there's all kinds of different levels that these electrons can jump at. The levels of the complexity of a solid object is so great that it emits lines all across the spectrum. Imagine there's a line there, and there's a line there, and there's a line there. There's so many lines that they blend into one another, and you get a full spectrum. So a solid object will give you a full spectrum, what we call a full spectrum, and it goes all the way across. It emits all the way across. What it is, it's just millions of lines that bleed into one another, and that's what you get if you heat something that's solid to a high temperature. If you take a solid filament in a light bulb, y'all know, have you ever looked at a light bulb and there's that little thing going across? That's what heats up, and it's solid, so it heats up and it'll give you all colors across the spectrum. Now, here's the cool thing. If you take a hot source, like a light bulb, that gives off a continuous spectrum, but you shine the light bulb through a gas, like, for instance, hydrogen gas or helium gas. If the light bulb is shining through the gas will absorb the light coming in. This absorption spectrum is like the opposite effect of me jumping down and throwing the photons. It'd be like you throwing the photons to me. So you throw me the red, watch what happens. Because I absorbed the light. This is a photon. When I absorb the light, I go up levels. When I jump down levels, I give off the light. When I absorb the light, I jump up levels. You see what I'm saying? What if you wanted to get me up to this top level? What would you throw me to get me up to the top level?
Blue.
Blue.
Throw me a blue. Got it?
Yes.
I'm so scared.
What's another way you could get me up to the top level?
Throw my red and the green.
Throw me the red
All
first.
three of them will go.
Throw me the red first. Red gets me up to the first level. Green gets me up to the second level. See what I'm saying?
Go to the podium.
I can't balance on the podium. So, oh, wait. If I go down, I gotta throw it back. So, green, red.
Yeah.
Isn't that fun? Oh, green, I gotta go back up. See? So, when you absorb, when gases absorb light, they go up in energy levels. And so what has happened here, When we take a heat source and we shine it through a gas, you will see the spectrum with lines missing. And what that means is the gas has absorbed some red, some orange, some green, and some blue. We call that an absorption spectrum. Most of the photons went right through it, but some of the photons were absorbed and made the electrons jump up energy levels. We call that an absorption spectrum. So what we can do is we can look in space at a hot object like the sun. Now the sun gives off pretty much a complete spectrum. But if there's a gas in between us and the sun, we will see the complete spectrum of the sun with some lines missing and know that there's a gas in between absorbing the lines. And not only know that there's a gas in between absorbing the lines, you can tell what gas it is by what lines are missing. You see what I'm saying? Like if we know that if that line and that line and that line and that line are missing, that it's hydrogen gas in the way, or helium gas in the way. You can tell what gas it is by what lines are missing. Yeah?
But since the air is made up of like all of them, all sorts of gases, like in our atmosphere, how do we like concentrate it down to one gas? Do we?
No, we don't. What you would get is you'd get this full spectrum with all these different lines missing, and you could have a computer look at all those lines and tell that we have several different gases in the atmosphere. If you take here's a hot gas like nitrogen, like hydrogen, and there you heat up the gas, there it releases only these lines, and we can tell from experimentation what gas that was, because we can take in our labs and we can heat up gases and experiment on them. So, there's different types of spectra you have to know. A continuous spectrum, 10 points if you and your partner can tell me what releases a continuous spectrum. I'll do it fill in the blank. A blank object releases, a blank hot object releases a continuous spectrum. Yes, blue is correct. Yes, purple is correct. Yes, green is correct. Orange? No? Okay, listen, because this might be on a quiz if we had one tomorrow. A solid object releases a continuous spectrum, like the filament of a light bulb. A solid hot object releases a continuous spectrum.
It's hot?
It's hot. A solid, well, it's got to be hot enough to be glowing.
Okay.
Give me an example of something that would release emission lines that looks like this. I'll give you that. I showed it to you earlier. What releases emission lines that look like that?
Wait, is it a missing line?
Emission lines.
Is it that chart missing?
I don't know.
It might be.
Is it a gas?
Yes, green is correct.
Yeah, I think that's right. I think that's right.
Blue, what kind? What kind? What exact? Those lines are from something.
It's either that.
Purple, not right or wrong. Anyone else?
I think that's right.
Blue, not right or wrong. Okay, I'm gonna give blue and purple. I'm gonna give blue and purple. Anyone else? This is the hydrogen emission spectrum. This is a gas, a glowing gas like hydrogen, that releases just a few lines because it's just got atoms jumping down energy levels.
Is that why it's missing the helium?
Is that that's not the helium spectrum, is it?
No, I said is that why it's missing the helium?
Is it? It's not helium, so it doesn't have the helium lines.
Which line then is the hydrogen line?
Hydrogen has all these lines.
Does helium have all
Let's
those
go back and
lines?
look at hydrogen. Here's hydrogen. Oh, hydrogen didn't have a blue, it had a green, didn't it? this is hydrogen, so it's got the red and a light blue and a blue and a purple. So I don't know what gas this is. I don't know what gas that is.
Could be nitrogen.
Nitrogen gas is a lot more complicated. Here's nitrogen gas. This was nitrogen.
Oh, okay.
Nitrogen's a lot more complicated. So, absorption lines like these would be seen when you have a blank between you and a hot object. Absorption lines like this would be seen when you have a blank between you and a hot object.
Okay.
Yes, purple
I
correct.
don't know, I don't know, but
Can you repeat the question one more time,
Do
Pro?
you have any other guesses?
Pro, can you repeat the question one more time?
yeah, the beginning.
And absorption lines like this, whoops.
Oh.
Absorption lines like this would be seen when you have blank between you and a hot object.
That's not it.
Green is correct.
I think that's not it.
Blue is correct.
Alright.
Can you repeat it one more time? I'm sorry.
Absorption lines like these would be seen when you have blank between you and a hot object. Orange, not right or wrong. Anyone else?
Ivy was
What's that gonna be about?
Bertoni and are most likely to have the most social media.
Pink, not right or wrong. Okay, let's look at this. Those of y'all that missed it, take a look. An absorption, you get absorption lines when you have a cool gas between you and a hot. Here's the hot object, it has to go through the cool gas for you to get the absorption spectrum.
It's the right idea.
So the cool gas will absorb several of the lines. And then the cool gas will start to heat up. The cool gas would start to heat up and would absorb those certain lines until it got hot enough where it started emitting and turned into a hot gas and emitted those lines. As the electrons jump back down, it would emit those lines. Here's something else we can tell when we look at objects with spectroscopes. If you notice, these lines here are shifted in this picture. Notice they're shifted upwards a little bit. See the arrow moving them up? Objects that are moving towards an observer have what's called a blue shift. And objects that are moving away from an observer have what's called a red shift. We call this the Doppler effect. Have you ever heard of that before?
Doppler radar?
Like Doppler radar uses the Doppler effect. So do cops. You ever wonder how a cop knows how fast you're going? He shoots radio waves at your car with his radar gun, and they bounce off your car, and they come back at him. And the way the wavelength of the radio waves is shifted will tell you how fast you're going. Will tell him how fast you're going. If you're coming towards him real fast, the radio waves will be squeezed tighter, and you'll have shorter wavelengths. If you're going away from him, the radio waves will be stretched out, and you'll have longer wavelengths. And the machine can tell by how the wavelengths are stretched exactly how fast you're going. And you can see all these little lines have been shifted upward. They've been shifted to the red. That's called a redshift. And that means the object that you're looking at is going away from you. Isn't that interesting? We can tell a lot of things about objects. You want to look at some of these lines through a spectroscope? Come into the lab. You can stop filming now.